So with the dynamic control response, the right keyboard arrow initiates a right roll of the albatross. The left keyboard arrow initiates a left roll of the albatross, with the downward arrow initiating an upwards pitch and the upwards arrow initiating a downwards pitch. Similarly, for the rudder controls, it's controlled with the A and D letters on the keyboard, with A causing the albatross to your left and the D causing the albatross to your right. Thrust is controlled using the W and S keyboard buttons, with W increasing thrust and S decreasing thrust. As thrust is increased, the albatross approaches a force meter, and as can be seen on the flight instrument, as the RPM increases, the corresponding force produced by the thrust increases as well. Up on the screen now is a graph of thrust and RPM. The test was conducted using intervals of 5 RPM, starting at 0 and going all the way up to 100 RPM. As can be seen, the relationship between RPM and thrust maintains quite a linear relationship, which is expected of the albatross UAV. For the right roll, the left aileron is deflected downwards and the right aileron is deflected upwards. This causes an increase in lift on the left wing and a decrease in lift on the right wing, which causes an overall right roll. For the left roll, the right aileron is deflected downwards and the left aileron is deflected upwards. This causes a decrease in lift on the left wing and an increase in lift on the right wing, which causes an overall left roll. For the downwards pitching, it can be seen that the both elevators are deflected downwards, which causes an overall downward pitching moment. For the upwards pitching, it can be seen that the elevators are deflected upwards. This causes an increase in lift acting on the albatross, which causes an overall upwards pitching moment. For the left yaw, the left elevator is deflected upwards and the right elevator is deflected downwards. This causes an overall yawing moment in the left direction. For the right yawing motion, the left elevator angle is deflected downwards and the right elevator angle is deflected upwards. This causes an overall yawing in the right direction. This video here shows how the weight and balance of the albatross UAV varies as the CG position is altered. Then, using the weights of the nose gears acting on each individual balance, the overall mass and centre of gravity of the albatross can be calculated. Using this example of the weight distribution, I will now show how the overall mass and CG location can be calculated. This is the MATLAB script created in order to calculate the overall mass and CG location. These are the outputted results of the mass and centre of gravity location. As can be seen, the value is very close with minimal error to the actual mass of the albatross. As can be seen from the graph of CL against alpha, between angles of attack of -10 to 8 degrees, CL increases linearly with angle of attack. As is expected, at higher flap setting, the value of CL is greater than at lower flap settings. However, at angles of attack greater than 8 degrees, it can be seen that there is a significant decrease in CL, which indicates that the albatross experiences a severe loss of lift beyond angles of attack greater than 8 degrees. This graph demonstrates a typical drag polar graph. As is expected at higher flap settings, the value of CL is greater than at lower flap settings for the same CD value. This is a graph of CM and CL at different CG positions as a percentage of mean aerodynamic chord. This is a graph of CM versus CL at different elevator inputs, with the blue line representing an elevator deflection of 0, red line representing an elevator deflection of -15, and orange line representing an elevator deflection of 15. As can be seen with the elevator deflection of -15, the CM values are much lower than the other elevator deflections at the same CL values. This indicates that trim conditions at an elevator or deflection of -15 are achieved much sooner than the other elevator deflections. This is the graph of lift to drag ratio against CL. This graph does not look as typically would be expected for a lift to drag ratio graph. The typical shape would be sort of a S-shaped graph. However, this, as you can see, is a lot more of an obscure shape. It's unsure why the graph actually has this shape. Up on the screen now is the ground handling of the albatross. Unfortunately, the frame rate is not very good. I apologise for that. However, it can be seen that the albatross manoeuvres as expected using the rudder controls. This video here demonstrates the minimum unstick speed for the albatross. It was found that the minimum unstick speed for the albatross was 17 knots.